So the correction from last time. So we talked about Kalan-Semantic equation. Kalan-Semantic equation, and then Kalan-Semantic equation involved this gamma. And this gamma is defined like this way: delta plus beta b hat. Where b hat is just acting on phi I of x is the differential of with respect to GA. Phi I of x. So this is the action of the b hat. And this is called anomalous dimension because delta measures classical dimension. Delta, this one measures classical dimension, scalar dimension. And this guy, of course, as you can see, so it involves beta function. If beta is not zero, this will measure quantum correction. So this involves quantum correction measure. Quantum correction acts on the operator. So therefore, this is called anomalous dimension. Because it measures the classical dimension, the deviation from classical dimension by quantum correction. That's why it's called anomalous dimension. Whatever happened, the quantum dimension of the Sator. So as I mentioned, this Sator is a trace part of the stress energy momentum tensor. This one is always 2, including quantum correction at the quantum level. So therefore, to get this 2, you need to define operator gamma O A is equal to gamma B. Like this way. If you define gamma axon like this way, then you can show that the so recall that the Sator is equal to sum of beta A and the operator A. So this is the relation between Sator and the perturbation of the theory, and then plug that on. So if you act gamma acts on Sator, and this gamma, sorry, I think I made again, my note is a bit strange. The 2 pi is strange. I thought I correct everything in 2 pi. Let's move on. Delta hat. Yeah, that's okay. Plus sum over also beta A GA acts on sum over beta A operator A. So instead of b hat, I just write down the with respect to derivative with respect to carbon constant, and then we just act on the 1 by 1. So so this operator is gamma. So therefore, this can be understood beta A gamma hat acts on operator O A plus this can see the beta. So therefore, you have the sum of beta A, beta B, derivative G of B. So this is what's going to happen. So this can be understood gamma. So the gamma acts on O, but instead, so this derivative with respect to G can see the beta. So therefore, it can act on it. Okay. So then, if you proceed, And then you just apply this rule into here, and then what you get is sum over AB beta B to delta AB minus derivative of beta A Okay, so then this guy counts out, this guy counts out, this guy counts out, what's left is this one. So therefore 2 times theta. Okay, that's how you get the 2 times theta. So therefore, always including quantum correction, this theta, capital theta has to be dimension. Scaling dimension has to be 2. By imposing this one, you can determine the explicit form of this gamma hat acts on any operator. And the theta is indeed just perturbation of the theory. Okay. So that's how you obtain. So we will use this relation later. This is a part I didn't explain last time very well. So I just added the explanation. And of course, if you use the so we know that the first orbit of approximate classical scaling, this is like this way. So we know, more precisely, beta function is 2 minus delta A G A. This is the beta function at the leading order, and you plug that one into here, and you can just see plug this one into here. You can see this is gamma hat acts on operator A, and you just get the classical dimension. So this is leading order. So this is just obtained by classical scaling. You get the delta A. So this is classical. This is classical dimension, scaling dimension. But if you try to include more quantum correction, this is classical analysis, and then a lot of correction will appear by quantum correction. If you include this one, you will receive some quantum correction here. That's why it's called anomalous dimension. Okay, so this gamma hat is called anomalous dimension. So that's the correction from the 6.14, my lecture note. You don't need 1 over 2 pi. I made a mistake. Okay, and now we start talking about the Zamoyski theorem. So Zamoyski theorem is statement. If you use the rotational symmetry, assume and the unitarity, series unitary. And then, I forgot. And then, okay, energy momentum conservation. In 2D, so there exists a function C such that exists such that monotonically or non-increasing. And moreover, fixed point C's fixed point is the central church. Of the IR fixed point, okay? RCT. So that's a theorem by Zamoyski theorem, and we try to show this theorem by using Cannon semantic equation. So again, T is so this is 2, 0, 2, 0. Theta is 1, 1. T is equal to TZZ, so therefore 2, 0. And theta is equal to TZZ bar, essentially. So therefore 1, 1, and T bar is equal to TZZ bar. Okay, so therefore it's a 0, 2 component holomorphic. And from here, if you consider the correlation function, so you have the, by Lorentz invariance, you should have 1 over z to the 4. But here, this one is dimensionless, essentially. It becomes dimensionless quantity. Even though it has a dimension, so this z squared is essential radius. Okay, so we assume rotational symmetry, so numerator should have dependence on only r. Okay, rotational symmetry. So it's only depends on radius, the function of radius. So, but radius also has the dimension 1 over mass, right? 1 over mass. But the theory is not conformal. Theory is not conformal. We are considering because that's why theta is non-zero. If it is conformal, theta is non-zero. Okay. If it is conformal, the trace part is non-zero. Okay. So therefore, if theory is not conformal means there is a there is some length scale. Theory has some typical length scale, mass and so on. Mass. Therefore, implicitly depends on this is also the mass scale. Mass of the mass scale the theory have, and they cancel each other. Okay, the dimension cancel. Z square has 1 over mass square, but this can cancel with mass, but it becomes dimensionless quantity, the numerator. The same thing. So I just implicitly this numerator implicitly depends on mass scale. This is also the same. So the numerator should be dimensionless quantity. By canceling this is the mass scale the theory have and then radius. Okay, and this is a form of the correlation function that will tell us the assumption of rotational symmetry and the dimensional analysis. Dimensional analysis, you should get this. And then using energy momentum conservation, you will get this quantity f dot plus. So energy momentum conservation will tell us this one is 0, and also we have g dot. So this is homework, which is very straightforward. Minus 1 over 2 h equals to 0. Okay, so we use assumption. Okay, let's go. Assumption 1, assumption 2, assumption 3. So assumption 1 will tell us this one. Assumption 1. So we use assumption 1 because it only depends on the radius, right? So that's rotational symmetry. And this is assumption 3. Assumption 3. So you use the energy momentum test. Essentially, what we used is this guy. We just use this one to derive number 3, this equation. And then we introduce the quantity C is defined as the 2f minus g minus 3 over 8h. Then we can show by unitarity. So since by unitarity, this function h has to be always non-negative. Okay, non-negative. So it's a 2-point function theta, so it should be unitarity was assumed will give you the if you use how to say last time I derived right so then yes, assumption 2 will tell you the c dot is equal to minus 3 over 4h. So plug this one into here, you get this one, and then so c dot is minus 3 over 4h. H has to be positive or non-negative. So therefore, this has to be always non-positive. Non-positive. So then what you get is a function, non-increasing statement. So, and the Kalan semantic equation. So Kalan semantic equation, C is just function. C is just function. Dimensionless quantity. Therefore, if you apply the Kalan semantic equation to C, so this doesn't act on C. So therefore, what you get is current semantic equation acts on C is indeed R is just Z R partial R minus sum over beta A GA acts on C is equal to 0. So this is the current semantic equation acting on the function of C, capital C. And moreover, we can apply the current semantic equation on this. So this is this is homework. This one is homework. This one derivation is homework, and derivation homework. This is actually very simple. Apply the current semantic equation on this theta correlator, which is beta A, beta B operator B sum over AB. Okay. So this is what you obtain from this relation I have written there here. So this one. So apply this current semantic equation on this correlation function. What you get is indeed beta A partial GA C of G. So C of G. I mean, of course, so you can use this relation. So this is equal to I think this is assumption. Assumption is that sum over A is R partial R, and then C of G. Yeah, of course it depends on R. And then, of course, you can use the definition of C dot equal C dot here, okay? C dot is minus 3 over 4H, right? And H is the numerator of this one, okay? Numerator of this one. Okay, so therefore, you can apply just current semantic equation this theta bar, and use the definition here. What you get is minus 3 over 2. So this is almost telling the answer of this homework. Beta A, beta B. Of course, I assume this one is 3 over 2 sum over AB. And where the GAB is called homological GAB is equal to R to the fourth, R to the 4 partial A partial B 0. No, partial, sorry. It's operator, sorry. Operator A and operator B. So since we use this correlation function, current semantic equation acts on this correlation function, so we just use GAB as the 2-point function of these two operators. Okay. So this is called Zamochkov metric. And then, so you can obtain this equation. Of course, we know that this one is positive definite, so we impose unitarity. So therefore, OA, the 2-point function OA and OB is the positive definite. Okay. So therefore, GAB has the inverse metric. Okay, GAB is the invertible metric. Okay, because of this unitarity. What is the answer? So detailed derivation is homework, but I'm almost, so just apply this current semantic equation, this 2-point function. by using this relation, you get this one. So this is homework to show. So then, if you use the apply the G beta A, apply the G inverse metric on this equation, what you get is GAB inverse so what you get this equation. Okay, so that's how you get it. And this is indeed the gradient equation. So it's called so gradient equation. So gradient of most function. So here you can consider as the you can consider whatever space of metric space of the space of coupling constant. So the space of city. So if you consider space of city GA. Okay. And then C is this space of coupling constant. I don't know. In general, it's a infinite many, but yeah, the space of coupling constant and the most function is a function of this function on this space of coupling constant, and the beta. Yeah, I mean, so GAB is a metric on this space of coupling constant, and you have the whatever gradient vector field, or maybe I can just write down a bit more schematically. So if you just have so you can consider there must be there may be a topology. So this is a space of coupling constant GA. And then you can consider the function as a most function C. It's like a height function, can be understood. It's just a map from the space of coupling constant to some R. Okay? And then so you can just have the map as a function like this way, as a height function. And the gradient vector field depends on which way. It depends on. You take this is since there's a minus sign, I think it's just that goes to gradient vector flow is moved like this way. And the fixed point is indeed when gradient this derivative becomes 0. Okay, fixed point is therefore fixed point is here. So. So last semester, if you take my course, you already learned this this thing. These 4 point fixed point of the this gradient flow, and then most index is 2, 1, 1, 0, and so on, and which is determined by Hessian of this most function. Okay, so therefore, so Zamoshkov metric GAB is a metric on this space of the coupling constant, and then when beta function becomes 0, it's really fixed point of this gradient flow of this most function C. Okay, so that can be understood, and in the fixed point you can see the IR fixed point. Okay, IR fixed point. The zero becomes conformal. And moreover, now I can erase this one. so we know at the conform fixed point, conform fixed point theta will become 0. It's because conform or trace becomes 0. Okay, trace of energy momentum tensor should be 0. Therefore, the correlation function only C only top one. The top one we know TTLPE. TTLPE is now only holomorphically dependent. Holomorphic dependence. Okay. The stress energy at the fixed point is holomorphic dependence, only holomorphic dependence, and we know from TTLPE this is the case. Okay, and the rest becomes 0. Okay, therefore this becomes 0. So therefore, so H becomes 0. So C dot is 0. Okay, C dot is 0. So therefore, it's a fixed point. And moreover, from the definition of C, indeed C, capital C, a fixed point G star is indeed 2F, and F is now C over 2, which is small c, central charge of the RC CFT. At IRCFT. So this is the derivation of the thermal theory. So therefore, C of G is always greater than C of G star, which is equal to CIR. Okay. So therefore, under the renormalization group law, so the function C is non-increasing, so most likely just decreasing quantity. So therefore, since from UV to IR, you have to integrate out all the massive field, okay, massive field. So integration. So renormalization group is just a coarse graining, okay. So therefore, you just go to low energy. Therefore, if there is a mass, whatever energy scale, and then whatever low energy IR. So this is, let's call it 0 maybe, then 0, and you start with high energy UV. So which is 1 over A. So we start with size size lattice A, and you just do the coarse graining, and then you go to IR, and 1 over whatever, 1 over R. If you go to IR, there's a mode which in between you cannot see. So there's a massive states. You cannot see massive states. Okay. So you have to, in the Feynman path integral, a Feynman path integral is d phi of mode k. So if you go to the Fourier momentum mode, k is integrated out of 1 over A to 1 over R. Okay, 1 over R. If you go from UV to IR, okay, you have to integrate the mode between them. Okay, so therefore you integrate out, you lose some information. Okay? So therefore C can be understood as C, the quantity that encodes the physical degrees of freedom. So encodes the degrees of freedom of the theory. Okay? So therefore, you always have a C UV is CIR. So this is the very important theorem by Zalotchikov in 86. This is the 86 by Zalotchikov, 86 in 2D. And 40, and this actually is the same thing. You can see the 40, 2011. There's a quantity called A. You can, in addition to central charge in 4 dimension, you can also introduce so-called A. It's hard to explain. I mean, if you don't learn the. So this, I mean, you can introduce some quantity similar to central function C in 4 dimension. So this is proven by Zohar, Komodowski, and Schwimmer. And sixth dimension, in supersymmetric case, with supersymmetry, you can see the similar statement, which is 16. 2016, you can also introduce the same quantity, like a A or whatever you call it. Let's whatever. I don't know. Let's go gamma maybe. With supersymmetry, you can introduce the quantity like this. So this one is the Cordova, the Mistrescu, and the Intrigator. And also, Joyan in our department is also working on this kind of stuff. Before he joined to, he recently doing different thing, but he also working on this kind of stuff in 6D. Good question. Odd dimension. There's another quantity called odd dimension. I mean, here we really use the good question. We really use the evenness of dimension, because I mean here we have the d square. Everything depends on d square and so on. This is and also the scaling dimension z04, d cube, and z bar. Everything depends on like a two-dimensional. And also, r dot partial r also works on the even dimension. But if you in odd dimension, things become subtle. But with supersymmetry, one can also introduce even odd dimension, the similar quantity. It's called F theorem and so on. But yeah, things are a bit more subtle in odd dimension. Anyway. And if you're interested in this kind of stuff, I think Joyan is more expert than I am. So yeah, you can ask him. Especially he did very good work in 6th dimension. Okay. So that's the geometrical system I didn't explain very well last time. Any question? Okay, so I will take a vote for advanced topic. So I'm going to move on from now, the so-called Lanagizev CFT correspondence. So from now, I think we will finish today Lanagizev CFT correspondence. So more precisely, so we will consider Lanagizev book a minimal model correspondence. From now, and after that we will move on to West-Zumino-Witten model. West-Zumino-Witten model. Yeah. And then good news is that after West-Zumino-Witten model, we will move on to advanced topic, which you can determine. And since there are many auditors here, so I would say registered students can only vote, participate into the vote. And as I mentioned, so one is entanglement entropy, which already, actually 3 years ago, or 3 or 4 years ago already, I also take a vote, and at that time students took entanglement entropy. And then this time I will take a vote. So one is entanglement entropy, second is integrable system, third is Kita F work, and just write down your name. No preference, write down. Only registered student can participate in the vote. And only you can add one. You can vote in one topic. And we will see which which topic students are interested in after West-Zumino-Witten model. And then advanced topic, there is no homework for advanced topic. So yeah, 3 years ago students speak entanglement entropy, but we will see. Okay. So entanglement entropy, there's already note. There's already note for and you can see the. Oh, by the way, I updated lecture note a lot, so you should take a look at the updated lecture note. But otherwise, I will write the new topic on the lecture note. If you pick some other topic, we'll see which one you're interested in. But if you pick entanglement entropy, I just improved my note. But otherwise, I will add new contents to the lecture note. Okay, so if you just can read my lecture note, you don't need to pick the entanglement entropy. So it's already written. If you want to learn some new topic, you can pick some other new, whichever you want. But entanglement entropy is a very hot topic. We'll see which ones. Okay, let's move on to minimum model correspondence. Okay. So Zamolchkov, so minimum model was introduced just by representation of Virasoro algebra. Okay, and then Virasoro algebra, when there are only finite many primary field appear, and then Zamolchkov again, I mean, he's genius actually. I mean, Zamolchkov and Kadi made a huge contribution to the CFT. Kadi and Zamolchkov, so I mean, you cannot study without to the CFT without reading or looking at their work. Zamolchkov and Kadi are wonderful, yeah, no, just wonderful. He just gives some Lagrangian description of minimum model, Lagrangian description, which is called random theory. So S is equal to d squared z, and then 1/2. Sigma is here is a field, actual field. So it's sigma is field. It's just a scalar field with potential. Okay. So this is Landau-Gibbs model. Usually Landau-Gibbs model is described as the theory without gauge field. Okay. So there's no gauge field, only scalar field. Huh? Oh yeah, yes. Sorry. Yeah. So this is kinetic term and the potential. Yeah. And the potential takes it's just a polynomial function of sigma. It's polynomial function z1 sigma plus z2 sigma square and so on, and g and of course you might wonder, there's no sigma 2p minus 2p minus 3. And this can be gauged away. It's called gauged away. Sigma goes to sigma plus constant shift. If you do the constant shift, even if you include this term, some whatever g 2p minus 3, and plug that this one into here, this one into here, and then tune the nice constant, you can gauge that way. So you can get rid of this constant. That's easy exercise you can do. I mean, if you just wondered, yeah. I mean, for instance, when p equal to 2, when p equal to 2, this is g sigma square, right? So the function is essentially g1 sigma plus g sigma square. But if you shift like this way, sigma minus 2 over g1 square plus g1 sigma minus g1 minus 2g. This term will go, right? Go on. Just look at the cross term of this one, cancel with this one, okay? And the constant shift of potential doesn't matter. It's just overall scaling of sigma. See, sigma is just field, the scalar field, or whatever. People usually write on phi or something. I don't know. It's just notation. sigma is just field, scalar.
Field has something special or any features?
It's just scalar field. So there is spin zero field. I don't know. I mean, usually people just write down like this way, but from now on, I will use correspondence minimum model. So minimum model, I use this phi 1 RS as a primary field. I just want to distinguish phi RS and then this scalar field. That's why I don't use phi. Okay, so that's the thing. So you can gauge the way for this 2p minus 3 piece. You can gauge the way. So gauge the way by sigma times constant shift. Okay, and then if you assume this is positive, so this is positive again, so this potential look like whatever, like this way, in generic term. In total, P local minimum. P local minimum for this. So this is called Lambda-Gibbs model. So this is called Lambda-Gibbs model. Lambda-Gibbs effective filter, whatever you call it. So Lambda-Gibbs, when physics terminology, it's just a theory with scalar field, quantum field theory with scalar field. So as you can see, so you can have the information parameter so these are deformation of the potential. So if you don't have this middle term, or if you have only last term, all the p local minima shrinks to like this way. It's degenerate minima. Okay, p degenerate minima. So if there's no, so this is when it's just b sigma is equal to g to the sigma to p minus 1. It becomes just local. It's just one minimum. Everything degenerate. But if you perturb the potential by adding this 2 times p minus 2 scalar field, you can just perturb this potential in the p minus 1, p local minimum. Sorry, p minus 1. Sorry. You should correct me. P minus 1. Okay. P minus 1 local minimum. So therefore, these are called relevant field. So this is a relevant perturbation. So these terms are relevant perturbation. Theory. Okay, relevant perturbation theory. And then if you look at the minimum model MP, so minimum model MP. So we know unitary. So if you look at the minimum model, indeed, there's a primary field. This is exactly the same as 2p minus 2 primary field. With the component dimension. Dimension less than 1. So therefore, and among them, so we have whatever 1, 2, 3, 4, 5 RS in minimal model, primary field with one small intercept and p equal to 6 is like this: 1, 2, 3, 4, 5, 6. 5, 6. And this 1, 1 is always a vacuum identity operator. So phi 1, 1 is always vacuum. And then so you know the formula for a compound dimension Rs is equal to, I already forgot. You should correct me if I'm wrong. As far as I remember, did I? Oh my goodness, I don't remember. I think 4. Is it correct? Let me check my lecture notes. I didn't print out that part. Conform dimension of minimum model. Yeah, -1. Okay. So this is conform dimension of minimum model. Conform dimension of primary of phi Rs in minimum model MP. And then lowest dimension is when R is equal to S is equal to 1, indeed. Then this part becomes 1 square and it becomes 0, right? 0. So therefore you can identify the vacuum. But next, the lowest conform dimension is actually R and S is equal to 2. So you can just plug that one into here, and what you get is indeed, let's do the computation like this. 4 times -1, 4 p plus 1. Yeah. Sorry. So this is 2 and p cancel, right? And then it becomes 2 square minus 1, and so therefore the conform dimension of phi 2, 2 is this one, 3 over 4 p plus 1. So that, as you can easily see, when p is usually greater or less than 3, right? Or equal to 3, greater than or equal to 3. So therefore, this conform dimension is less than 1. Okay, phi 2, 2 is less than 1, and also if you take the how to say, the fusion rule, if you use apply fusion rule, 2, 2 is indeed, you can just obtain identity plus phi 3, 3 plus phi 1, 3 and plus phi 3, 1. And if you use the conform dimension written here, the lowest conform dimension, this guy, apart from 1. Apart from 1, lowest conform dimension is phi 3, 3. And if you compute phi 1, 3, phi 3, 1, actually this is dimension, conform dimension greater than 1, indeed. You can just plug that one into here, and you can compute, you can show that this is greater than 1. And this is the almost 1, you can compute. But this guy is much smaller than this guy, conform dimension. You can just check. Therefore, so if you do the how to say, multiplication in fusion rule, fusion multiplication or fusion ring, it's called, sometimes called Faraday algebra. So what you get is phi 3, 3. Next is phi 3, 3. So you have phi 3, 3. And if you compare with the relevant part, so as I mentioned, conform dimension of 1, less than 1 only appear in this part, in diagonal part, 5, 3, 3, 5, 4, 4, and then 5, 5, 5. And next is this guy, phi, I call it 2, 1 or 1, 2. Do I call it 2, 1? Yeah, I think 2, 1. 2, 1, phi 2, 3, 1, 3, 2, phi 4, 3, phi. Oh my goodness, my. Okay, so. Yeah, so this is p equal to 6, p equal to 6, and you can easily see that if you use this relation, relation of the conformal dimension, this is conformal dimension, you can just check only the conformal dimension less than 1 is this guy. So this is p equal to 6 case, p equal to 5 case, sorry. Huh? I'm sorry, I got confused. Yeah, this is p equal to 5, sorry, p equal to 5. I just got confused. And then, so how many? 1, 2, 3, 4, 5, 6, 7, 8. And is it correct that my claim is p equal to minus 2? Okay. I think I made a mistake. Okay, great. Here I call it, I think, so this is p and p plus 1 and p. So therefore, I see. Okay, I think my notation is, this is MP. I call it MP. So I should change the notation indeed. So this is MP plus 1. MP plus 1. Okay, MP plus 1 has the my goodness. No, sorry. Yeah, p minus 1, sorry. I think my notation, so here, indeed, p equal to 6 in this case, p equal to 6, indeed. Sorry. I think up to plus minus 1 is wrong in my lecture note. I was not careful. So here, so what I meant is here is p minus 1 is this one. Yeah. So I think I will change the notation in the lecture note. So just bear with me with this wrong notation. So this is the M6 and 5. Okay, M6 and 5 in my notation. So I call it, this is P prime, and this is P. Okay. And then, okay, so maybe I should call it the when, yeah. MP and P minus 1. Okay. So MP, so minimum model, unitary minimum P and P prime. You have 2 times P minus 2 primary field. So in this case, P is equal to 6. P equal to 6. P equal to 6. So therefore, you plug down into here. So you have a 2 times 4. 2 times 4 means 8. And you can check that there is the 8 primary. Less than. With conformal dimension of less than 1. Okay. So this is the case. So I will change the notation of the lecture note later. Okay, so sorry about the confusion. So now, so you can see that the primary field with conformal field dimension less than 1 is the 2 and the p minus 2 primary field, and then you can also see in this potential relevant deformation has the 2 times p minus 2 the relevant deformation. So we want to identify this relevant deformation with this primary field. Indeed. And then we will see the consistency check. That's what we are going to do. First of all, the lowest conformal dimension is, as I mentioned, is apart from identity is phi 2, 2. So therefore, so this should be identified with sigma operator in the first one. And if you take the OPE of sigma of z and the sigma of 0, what you get is indeed z times yeah. I think I should call it z bar and 0, and then this is 2h22 and plus 1 over sigma 2 h22 minus h prime and the normal order sigma square. Okay, sigma square. That's what you get in the OP of sigma field. And if you compare with this, and of course there's a higher order correction will show up. Higher order correction will show up. Okay. So if you compare with this fusion rule of phi 22 and this OPE of sigma field, you can so 1 should correspond to this guy, and the phi 33 should correspond to this guy. So therefore, what you can do is the phi 33 can identify with sigma square and so on. 544. And if you do the fusion rule of the minimum model, you can just, so I mean, you guys do the homework, right? Fusion rule of minimum model. So you guys are familiar with how to do the fusion rule in minimum model and the sigma cube and so on. So what, in fact, so this relevant deformation and this primaries with the compound dimension less than 1, you can have 1-to-1 correspondence.
Oh, sorry.
Yes.
Can we have s greater than 4? So p prime is 5. So can we have s equal 5? Shouldn't we stop at s equal 4?
I'm sorry.
So r should less than 6 and s should less than 5, right? If we have p and p prime equal 6 and 5.
You are correct. You are correct. You are correct. You are correct. So what he mentioned is that usually, so R and S is, you are correct. Usually this is less than P prime minus 1. Okay, I also made some stupid conventional mistake in that case, P minus 1. So Archimedes is this one. Therefore, if you pick the 6 prime, P prime is 6, it shouldn't show up. And then likewise, if you pick P equal to 5, it should be less than 5. And that's what he meant. Okay, you're correct. I think I'm better. Then, okay, so then this is M76 in that case. M76. Oh, then it's everything okay. So I call it this is equal to MP, right? Yeah. Sorry, I think I didn't make a mistake. This is M6. And P equal to 6, right? Oh, okay. So this is correct. Sorry, my lecture note is correct. Thank you very much. Thank you very much. My lecture is correct. I was correct. So MP P equals 6. This is the case. Yeah. Thank you very much. I appreciate it. I made a lot of mistakes, so please confirm me. So yeah. So my lecture is correct. There is no confusion. P equal to 6. You only you have a compound dimension less than 1 is 8 primaries. There are 8 primaries, and then when P equal to 6, you have a relevant deformation, 8 relevant deformation parameter. And what we can do is you can identify the relevant deformation, and then this guy as 1 sigma square, sigma cube, sigma to the 4th, sigma to the 5, sigma to the 6, sigma to the 7. Okay, sigma to the 7. And then, of course, you can use the equation motion for this non-negative model. So equation motion is you can easily derive from, I mean, if you forget about this relevant deformation and then only look at this one, so the equation motion is indeed sigma is equal to sigma 2p minus 3. Okay, 2p minus 3. Okay. So this is leading term, g times, maybe g times. Okay, anyway, some constant is equal to some constant times. So you just have a derivative with respect to this sigma. You get the 2p minus 3 and then derivative, kinetic term coming from p. So this is equation motion. So therefore, when p equal to 6, this is equal to 9, right? I got confused. So this is sigma to the 8, right? And then, okay, so you can just identify the, So here you have the sigma 5 and the sorry, I got confused. Sigma to, what am I doing here? Sorry, I think I told you completely wrong thing. So this is correct. So this is everything correct. I'm sorry. I'm very disorganized. Sorry. Everything less than 1. Sorry. This is less than 1. Sorry. Yeah. So we know that so we exclude the identity operator as the perturbation. So perturbation. So relevant operators are these guys. So this, sorry. I'm very disorganized. I'm sorry. So the relevant deformation, this guy, and so there's 8 term that corresponds to this one. These are compound dimension less than 1. So this one is also less than 1. Sorry. So you can identify these operators with these primaries. These primary, and if you take the fusion rule 1, 2 times 2, 2, sorry. 2, 2 times 1, 3, you can take phi 2, 2 plus 5 p minus 2 and p minus 3. So that's what you get from the OPE. And indeed, you can identify this, if you take the, so if you, sorry, so phi 1, 3 is equal to 5p minus 1 and then p minus 2 by symmetry. Okay, so we can use symmetry of minimum model. You can identify, you remember, phi rs is equal to 5p minus r and p prime minus r and p minus s, as far as I remember. Yeah. Let me check. Am I correct? So if you can use the, let me check my notation. Sorry. Oh, yeah, the other one, p and p prime here. So here, p equal to 6. So therefore, phi 1, 3 is equal to phi, p is equal to 6. So therefore, this is 5, and p equal prime is 7, and 7 minus 3 is 4. Okay, so this one. So this guy, the last one is equal to phi 1, 3. Okay, phi 1, 3. And then, so therefore, so we just take the fusion rule, phi 2, 2, and the phi 2, 2, you get a phi 3, 3. Phi 3, 3, and the phi 2, 2, you get a phi 4, 4. And it's likewise, this fusion will give you this guy, and this fusion will give you this guy. And this fusion give you this guy, and this fusion gives, and this guy. And then we try to take this fusion with this guy, okay? That's what we are going to do. So then, so if you take the phi 2 and times, this is the same equivalent to 554, it's the same thing, you get the phi 2 and the phi p minus 2. Which means that if you take the fusion of this and this one, you come back this one. Okay? But however, the note that so it's the same thing, sigma and sigma 8, sigma to the 8, if you take fusion, you get the sigma 9, right? Sigma 9 to the 9. The equation motion will tell us sigma to the 9 is the derivative of sigma. Okay? So therefore, so here, what you get is indeed L minus 1, L bar minus 1, phi 2, 2. It's a conformal primary, so it's not necessarily the primary field. What you get is this derivative and the antiderivative, or whatever, holomorphic derivative, anti-holomorphic derivative, acts on phi 2. Equation motion tells us. Therefore, it's a descendant. It becomes descendant of phi 2. So this is equivalent to this mention that you get the equation motion of this. Okay. So this is the proposal of the Zamoshkov, and we can explicitly see this is correct by using Zamoshkov's theorem from now on. Okay. Sorry about lots of confusion. Yeah. Yeah. So these are conformal primary with less than 1, and then these are the. So there's a 1-to-1 correspondence. We will see this correspondence is it makes sense by using the Zamoshkov system from now on. Suppose you start with minimal model. So minimal model action is given by SP, is given by d square z, and 1/2 partial sigma square plus whatever g times sigma 2 minus 1. So this is indeed corresponds to minimal model NP. NP, and we correspond to NP, and we just perturb this action by relevant deformation. So phi 1,3, and you can check that the conformal dimension of H13 is equal to H13 in the equal to 2 minus 4 p minus plus 1. Okay, let's check this is true. If you plug that one into here. P minus 1 plus 1 HRS. So H13 is equal to P is equal to whatever. P plus 1 minus 3P square minus 1 divided by 4P plus 1. That's what you get. And this is equal to minus 2P plus 1 square minus 1, right? Am I correct? And this can be understood as 2p minus 1 square minus 1. So therefore, this word is 2p minus 2, 2p, yeah, 4p, p plus 1. Do you agree? Please correct me if I'm wrong. Do you agree with me? Okay. And now this is equal to why am I so side 2 times. So therefore what we get is this is indeed p minus 1 p, we have the p plus 1. Do you agree? Do you guys agree? And the p cancel, and this is equal to 1 minus p plus 1, 2. Do you agree? So therefore, if you multiply 2, you get that one. Okay? Of course, this so as I mentioned many times, the scaling dimension is 2, right? Scaling dimension of minus 2, actually. D squared x is minus 2. So therefore, relevant deformation should be, the dimension has to be, this is 2 times delta. So scaling dimension has to be less than 2 for the relevant deformation. That's why I keep mentioning this is the conformal dimension less than 1. Okay? That's why I keep mentioning the conformal dimension less than 1. So these are relevant deformation. Okay. And this is very close to 2. So this is, so as I mentioned, I already erased. This guy, 1, 3, always the last one. Corresponds to this last one. Okay. The last one. This 1, 3, as I mentioned, this can be identified with this guy. P minus 1. So this corresponds to, this guy corresponds to 5, P minus 1, P minus 2. Okay. Always. So this is the even though less than 1, but close to very 1. Okay. Very close to 1. And if you take the fusion rule of phi 1, 2, phi 1, 3, phi 1, 3, you get the identity operator, and then of course it involves a 3-point function coefficient, usually phi 1, 3, and phi 1, 5. And then indeed, so if you compute the 3-point function phi 1, 3, phi 1, 3, and phi 1, 3, of course you get coefficient, I call it C1, and then Z, essentially, whatever, Z1, Z2, Z3, 1, 2, Z1, 2, here is just a H1, 3, everything's same. H1, 3, Z2, 3, H1, 3, and G3, H1, 3. And this C1 has been computed by his name. Computed by, so I'm not going to derive, so that you can just take a look at this. C1 takes the following form. 4 over square root 3, and then 1 minus 3, it's 3 epsilon over 4 plus order epsilon square. Where the epsilon is, I just take this one as epsilon. So this guy I call it epsilon. So namely, I take the limit p is very big, p is big integer, and we assume this guy is very small. 4 over p plus 1 is very small. And then this 3-point function takes actually it can be written like a hypergeometric function type, it's more like a gamma function. So, and this one is the, I should know his name. Forgot his name. Yeah. Dochenko-Fateh. I mean, derivation I'm not going to explain, but let's assume this is correct. And now what we want to do is which conformal field theory. So we start with minimum model and perturb it by relevant deformation. Okay? And so therefore it undergoes some RG flow. And then at the fixed point we will have another conformal field theory. And we want to identify what kind of conformal field theory we will get. That's what we want to do. And then, so that's what we want to do. And as you can easily see, so in previous case, we identify phi 1, 3 is indeed this guy, right? Sigma 8. Sigma 8 indeed, as you can easily guess, this is indeed corresponds to this is indeed sigma to the 2 p minus 2. Okay. In this case, p is equal to 6, so therefore, yeah, my lecture is. Yeah, so the 2 times p minus 2. So the relevant deformation, what we are going to do is indeed we add this term into this Lagrangian. So essentially what we are going to do is indeed this is essentially adding the potential term plus g, whatever, 2p minus 2, sigma 2p minus 2. So therefore, if you add this term, so this term becomes actually indeed, under RG flow, this term becomes indeed the irrelevant, and what dominates is this guy. So therefore, so if this is dominate, indeed, this corresponds to the minimum model. What is p minus 1? Okay? So we just change p minus 1 to p minus 2. Okay? So therefore, we expect, if you believe this is Zamochkov identification, we expect if you start with MP with relevant deformation, it undergoes the RG flow. We want to see if this is correct, MP minus 1, by using Zamochkov system. That's what we're going to check. And then so what we are going to check is that you start with so let's call this is energy scale, whatever, and then space. So here is the space of two-dimensional theory, space of two-dimensional theory, 2D theory, Lagrange model theory. You start with the whatever, the MP, or whatever. You start with MP. And you deform by phi 1, 3. So this, so whatever. So this is space of 2D Lagrange model or 2D Lagrange middle. Phi 1, 3, which is sigma 2 p minus 2. You deform by the theory, and then it goes under RG flow. And what we want to check is the fixed point is MP minus 1. That's what we want to check. Okay. By Zamochkov system. Okay, so that's what we want to check. So, and it's a homework to show that the beta function of so this is homework. So beta function of G is this guy. This guy is indeed can be written as dg, d lambda, and this is homework. I think the derivation is the homework. Order g cube. So this is homework to show. I think I just give a detail one by one step to derive this one. So I hope you can derive this one. And then we can use the, so we know that the Zamochkov theorem tells beta Gc is equal to 6.26 is the, yeah, sorry. I think we can use this one. Is equal to minus 2 over 3, and then so we can have this some constant, yeah, some constant. So there's a metric part, some G inverse this one. So this is some constant. So therefore, if you plug this one into here and then do the integration, And what you end up with Cg is equal to Cp. Cp is the central charge of minimum model plus alpha times E over 2 G squared minus C1 over 6 G cubed and plus order G to the fourth. That's what you get. Okay. You start with the minimum model of P, so therefore central charge should have Cp. Do you remember Cp is equal to 1 minus, is it the case? I already forgot. Is it the case? Do you remember? I already forgot. Yeah. I think it's correct. Yeah, it's correct. So you start with Cp, and under renormalization group flow, the C becomes like a function of with coupling constant G. And now if you use this Zamash goes to this gradient flow equation, we don't know the coupling constant G inverse. Okay? Not coupling constant, the Zamoshkov metric yet. But we just consider this is just constant and plug this one into here. And just integration by G, you get the Cp plus alpha times this one. So remember that if you take the derivative with respect to G, you get the constant times this guy. Okay? Okay. So therefore, so we want to determine this alpha. Okay. So this alpha really depends on Zamoshkov metric. So C dot, and we know C dot is equal to minus, I forgot, H, 3 over 4? Sorry, 3 over 4? Yeah, 3 over 4. Okay? Where dot is indeed, I mean, this is indeed equal to R squared divided by R. So this is the case. So this is the definition. R is a radius. Okay, so then, and we know H is indeed given by theta term, right? Theta is equal to H, I think Z square and Z square. So this is R to the fourth, I think. R square, remember? Yeah, R to the fourth. Okay. And now, so we, yeah. So we know that so therefore delta C, so from here, delta C can be obtained by minus 3 over 4 infinity dr square, and R square, and then theta R, and theta R is 0. That's how you obtain delta C. And now, so we know the theta is just deformation. So we know theta is equal to this deformation G times phi 1, 3. G times phi 1, 3. So this is we know. So plug that one into here, and what you get is the 1 over 3 over 4. Why there is an epsilon appear here? Oh, sorry. This is beta. Sorry, beta times. Okay, sorry. So this is beta times phi 1, 3. So in beta is indeed the leading term is Eg. So therefore this is equal to Eg square dr r square, and then phi 1, 3 r and phi 1, 3 c. And we know this one is a primary field, so therefore we know the 2-point function primary field. So therefore this is equal to minus 3 over 2 Eg square, and then 0 d r and r cube divided by r 2 times h13. Delta 3? Yeah, 2 delta 1, 3. Okay. And we know delta 1, 3 is over there, here, written here. Okay, this guy. And plug that into here and do the integration, and just only look at the leading term of epsilon. And we will get to 3 over 4 epsilon g squared plus order e3. Okay, that's how you obtain delta c. Delta c. So from this equation, and we know the definition of this theta function, we can just obtain the delta c by using the 2-point function of primary field. Okay. So therefore, if you compare between this guy and then this guy, we know that the delta, the leading term delta is alpha times epsilon over 2, and the delta c is really this one. So therefore, from here, alpha is indeed minus 3 over 2. 3 over 2. That you can derive. So this from this analysis. So even though we didn't know the Zamochkov metric, by using this Zamochkov method and also Kalan-Semantic equation and then 2-point function of the primary field, we can determine R. And where's the fixed point? Fixed point is C G star. Fixed point is indeed beta becomes 0. Fixed point is the beta G star is equal to 0. This means fixed point is indeed G star is equal to 2e over c1. So just plug this one into here, you will see this is beta function dimension. This is fixed point. So therefore, what's happening is fixed point is C, and the fixed point is indeed Cp plus alpha is already we know minus 3 over 2. Then you plug this one into here. Cp minus 3 over 2, and then e over 2, 2e c1 square minus c1 over 6, and then 2e c1 to the cube. Okay, so this is the case. You just do the computation. Then if you do the computation, and the leading term C1, we know that, so we use the Dovchenko-Fatiev result. This guy. This guy. So we use the plug this one into here. Into here, what you get is indeed Cp minus e cube c1 square. Okay, sorry, Cp, and then you I just summarize this part into here. Okay, this is indeed, if you do the honest computation, you get the e cube or divided by c1 square, and then do the computation to plug this one into here. And this is equal to Cp minus 3 over 4 square. Yeah, 3 over square is leading term of this one. 3 over 4 square is the I think yeah. So the leading term is the this one. 1/c1 square is leading term is this way, and e cube is this one. So you just plug this one into here. Essentially, so we assume p is very big, so therefore 4/p to the cube. And this is Cp minus 12/p cube. Okay, do you agree? And then, so we know Cp is indeed this guy. So Cp is indeed, roughly speaking, this is equal to 1 minus 6/p squared. And plug this one into here. Therefore, C G star is equal to 1 minus 6/p squared minus 12/p cube. P cube. Why P cube? P cube, okay. P cube. And then, sorry, I got confused. And why this is equal to Cp minus 1? I think, but how do you get 1/p cube is this guy? I don't remember. Sorry. Okay, let's take a break. I will answer why this should be Cp minus 1. Let's take a break. I will tell you after the break. Sorry. So how about the boat? What was the result? So let's take a 10 minutes break. Oh. Integrable system. So after the boat, I will talk about integrable system. So more like Yang-Boxed Heisenberg chain and so on, I think. Just a moment. Directly? Oh, thank you very much. Direct calculation. Yeah. So how did it work?
This is
Yeah.
and you just calculate.
Thank you very much. Thank you very much. Direct calculation. Okay. Thank you very much. Okay, thank you.
方面可能是从对对是热热的这种东西。
I see.
然后它应该是继续往下做，就是把这个乘3次，它就出现的普通应该是最低的是最显示，继续往下上就发现这样子。意思是说，在R指数就像是，跟口风风景的是最低的最后一次口风一样，所以只能它这个。
Okay, so let's do the direct calculation and show you guys. CP. Yes.
I don't understand why we pick the lowest dimension term and identified with the scalar field. Why always the lowest dimension?
Why lowest dimension? I mean, if you take the OP of sigma and then whatever, C or R, this is 1 over R, and then 2 times delta 1, 2, 2 or whatever, 2, 2, and next is R, 2 delta 2, 2 minus sigma squared plus dot 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 dot. And then higher one can be identified this operator up here, okay? And the lowest one up here, then the first one that up here.
Okay. So to derive the correspondence here, we need to do the computation.
Yeah, so we do the phi 2, 2, and then phi 3, 3. And it should contain 5, 4, 4. It's the lowest dimension. And so on. And the next is phi 2, 2. So this is essentially sigma times sigma squared, essentially. And you get sigma cubed. And then, and so on. You just multiply phi 2, 2 recursively.
它是什么 RS 加上就 RS 大一些。哦，是减号。实在差不多大的话，实在不行就再最小单选。我为什么记不住？
话说，我想问一下，就是按这系统
Yes. Small gamma is a matrix.
So why do we express gamma OA at this form?
But to get this, so we know this theta is always dimension 2.
Yeah.
The classical dimension is always 2. So we want to gamma act on the theta is 2 theta. That's always true. To get this, and the theta is equal to theta is equal to beta O, beta times O, right? Operator. So plug that one into here. To get this expression, you need this one.
Oh. So the logic is at first we have this.
Yeah, this one.
And
To get this, yeah.
from this we know that gamma
Yeah.
acts on an operator.
Yeah.
It must have.
Yeah, we must have.
对应的原则就是把这个 fusion 的过程，把这个 field 的 P 的过程。
我还想着这样的生活还是它是不是就是关于方式？你就下一个对啊，你就拿 C 嘛，这样 C 个 G，C 个 D， 然后做一个大的，就不会是法律。
这里是 哦，对对对，对，然后这个是S小别好像会跟 relevant 它是不是说就是中国的话，它写的一个金管理这么多，这个model小对。
Okay, shall we resume? Shall we resume? Actually, this one is direct computation indeed. So the difference between CP and CP minus 1 is just a computation. Yeah, I mean just expression for central charge. Difference in central charge is indeed, yeah, of course, 1 cancels, overall factor 6 over p, 1 over p plus 1, minus 1 over p minus 1, and 12 and p cubed over p cubed. So therefore, this one will show that this one is indeed. Okay. So this is evidence by using the logical theorem, the central charge. If you do the relevant perturbation of the 513 and then flow to the IR, our fixed point is described by, this is one evidence, p minus 1, minimum 1. Okay? And moreover, so this is the, by using the logical theorem, and this is exactly what the Lamarck model tells us. I mean, once you perturb with this guy by relevant perturbation, you can ignore this guy, and then what's relevant to this guy, and this is equal to np minus 1. And moreover, so moreover, so as I mentioned, anomalous dimension is gamma acts on operator is indeed equal to delta 2 minus delta AB minus I think the acts on, so acts on A, so this is the operator B. And so this is the how the anomalous dimension acts on operator. In this case, only you have a one perturbation, so therefore, so you act on gamma, acts on 513. Okay. If you consider 513, and then you have a 2 minus beta over g, and then I think I erased beta, the expression beta, unfortunately. And then you recall the expression beta is equal to E g minus c1 to g squared. Plug that one into here. At the point g equal to g squared, g star, and the fixed point. We know g star is indeed given by this guy. So just take. So therefore, is E minus C1 G star. Okay. And plug this one into here, and what you get is indeed equal to, I hope I don't make a mistake, this is equal to E minus 2E is equal to minus E. Okay, do you agree? And plug that one into here, you get it becomes 2 plus E. Okay, you understand? So therefore now it becomes 513 is relevant operator at UV. Relevant operator UV. However, it now becomes irrelevant because it's greater than 2. Okay, conformal dimension is greater than 2. And in fact, so we know epsilon is indeed, roughly speaking, is indeed equal to 4p plus 1. So we plug into here, and this is equal to indeed 2 plus e p plus 1, and if, 4. And this is indeed 531. So this is, so therefore 531 in the theory. 531 in the conformal dimension of 531. If you compute, should we compute? So again, p plus 1 r minus p s square minus 1 over 4p and p plus 1. I think this is the case, right? And plug 3 and 1 here. What you get is 2p plus 3 square minus 1 4p p plus 1. Okay. So this is what you get. And then this is equal to this. R is equal to 3, S is equal to 1. And this is equal to 2p plus 4, 2p plus 2 divided by 4p and p plus 1. Okay. And then this is equal to, of course, p over p plus 1, p plus 2, sorry, p over p plus 2, okay, do you agree? And this is equal to 1 plus 2 over p, okay, 2 over p. And if you multiply 2, yeah, of course, if you assume p is very big, I mean, okay, so that very big, you can approximate p, so therefore you can have the conformal dimension of 532. So therefore, if you perturb 513, indeed 513 under RG flow, it comes back by 531 as a primary thing. Okay. The operator dimension, so as a quantum effect, you can easily see the dimension will change under RG flow. Okay, conformal dimension change by under the RG flow. That's why it's called anomalous dimension. The gamma acts on phi, measure quantum correction to the scaling dimension. So this is a very good example to understand the RG flow in 2 dimensions. So when I was the student, I read the Peskin and Schroeder, and then of course I think QFT 2 you will learn this Kalman semantic equation indeed. Kalman semantic equation and anomalous dimension in whatever in Peskin Schroeder like a chapter 11 and so on. I didn't understand that so much. I can derive like by reading, but I can derive the equation and so on. But I don't understand the meaning of this Kalman semantic equation. But after I learned this 2-dimensional example, everything becomes clear. So that you can really compute the conformal dimension of the relevant information, and after the RG flow, really the dimension changes due to the quantum correction and so on, and then you can compute the central charge by using the Zariski theorem or this gradient flow equation. You can check explicitly central charge at the fixed point is the minimum model p minus 1 and so on. So this is a very good example to understand the RG flow, even though I made a lot of mistakes by explaining. Kaishin helped me. So, so this is a good example to understand the RG flow, and I hope you understand what's going on, how the lambda model and the minimum model correspondence, and of course how this RG flow Zamochko's theorem will tell us about the space of conformal field theory, space of two-dimensional field theory, and so on. And of course, we can do the same thing, and you can again perturb the phi 1 3 again. Then you end up with MP minus 2, MP minus 2, and so on. And again, phi 1 3 becomes phi 3 1 in that theory, and so on. Yeah, phi 1 3 is of course, I mean, thanks to the Kaishin's help. So so you have 1 phi 2 2 phi 3 3 and so on, phi 5, and then phi 2 1. I call it 2 1 phi 3 1 3 2 and so on, and then phi you get the p minus 1 and p minus 2. So this is the highest component dimension. It's close to 1. The component dimension is close to 1, or scaling dimension close to 2. 2 minus epsilon is I call it. So this can be identified by phi 1 3. So you always have this kind of operator, phi 1 3 close to. And then you can just always perturb the theory, conformal field theory, by this relevant perturbation, and you end up with another minimum model and so on. So that's the good example to understand the renormalization group law by using Zamochko's field theorem and the minimum model and lambda model. So it's a very, 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 very good interplay between conformal field theory, renormalization group law, and then lambda model. Okay, so this is what I wanted to explain about this section, and I will move on to West-Zumino-Witten model. Okay, so after West-Zumino-Witten model, so I took a vote, so let me count. 1, 2, 3, 4, 5. 5 people wants to vote for entanglement entropy, and 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 people vote for integrable system, 1 people vote for Stein's work. So I will talk about the integrable system, mainly Yang-Baxter equation, and then Heisenberg chain, and so on. I think this is new topic. So I will write down lecture note for it. So for advanced topics, there is no homework. I think you guys already learned enough to the CFT. Basic, I would say basic to the CFT. I mean, I don't mean to, yeah, it's better not to give too many homework. You already did too many homework. In West-Zumino-Witten model. So, but West-Zumino-Witten model, you have homework. So I think including this one, 3 more homework. So because I will spend 2 weeks, at least 2 weeks for West-Zumino-Witten model. Okay. I call it West-Zumino-Witten model. Zumino. But actually, West-Zumino's work is indeed like a 70s. And then there is a work by Novikov. He's mathematician, a Russian mathematician. And he wrote even though he's a mathematician, he added some topological term to understand the topology, three-dimensional topology. But I think I only see this in his paper in Russian. And also at that time, of course, the Cold War. 82, actually. As far as 82 or 83. People didn't know his paper, and Witten in 84. Especially introduce the Witten model. So therefore, anyway. So West-Zumino's work is actually 70s. It's a higher dimensional case, and then Witten considered 84 in two-dimensional case. And Novikov also considered in two-dimensional case, but people didn't know. I mean, I'm not sure with the notes at the time of Novikov's paper. I don't think it's translated into English, but anyway, so people usually call with Zumi with the model or with Zumi Novikov with the model. Anyway, so this is the another instance of the 2D conformal field theory, and it's not only involves not only Virasoro algebra, but also so-called it's more like a current algebra, affine Lie algebra, and so on. So it's the theory becomes much richer once you introduce the Western middle with the model. And two-dimensional theory becomes much richer and then much more beautiful. The infinite dimensional Lie algebra becomes much more interesting. In addition to Virasoro algebra, you include more like infinite dimensional version of Lie algebra, which is called affine Lie algebra, Katsumudi Lie algebra, and so on. So that's a very important two-dimensional conformal field theory and exactly solvable. For instance, coordination function can be determined by so-called equilibrium geometric equation, and so on. So that's what we are going to learn. To introduce the Western middle model, actually let's go back to free boson. So free boson, as we already learned, is d square x. Or maybe you can just write down. Okay. That's holomorphic component you can write down. And this action has a symmetry phi goes to phi plus constant shift. So this is of course the symmetry of the action. So the net current is you can just take the. I mean, you can easily see that the it's just a net current is indeed. I mean, it's just a this one, but somehow normalization is something like this one in my lecture note. Anyway, so you can easily see this one. Well, maybe I call it Z. And of course, the conservation of is really this one. Okay, so this is the conservation current. So therefore, for this symmetry, the current is the you can just take Jz as the I times phi J bar C bar is equal to minus I phi bar phi. Somehow I take this one. And then we know that the T of Z can be understood as minus 1/2 and this can be written as the indeed JJ current. And then this is indeed I mean I'm doing very simple thing. It's a free boson. This can be written as follows. G is indeed, so you can introduce so-called U1. Okay, U1, okay, people said U1 group. U1 group is just a complex number. Whose, so this is U1 group. So therefore, so it's just circle. It's just circle, and the group row is just rotation. The group row is just rotation. Multiplication is just rotation of the. And this can be written as the, of course, e to the phi. So phi, G is defined Z bar is mapped to like this one. This is U1 body, right? Where phi, I assume phi is a real scalar. Okay, I assume real scalar. So then this is the here also it's I assume phi is a real scalar. If you introduce this notation, we can have this action can be written as 1/8 pi d square z g inverse. So you can write down like this. So that's easy. You can easily see that. So this is the right way to formulate the action of free bosons. So here G takes the value of U1 gauge group. Okay. So U1 rotation, and this symmetry is just a e to the I phi goes to e to the I phi plus constant. So therefore, it's just complex plane. I mean, U1 is just as I mentioned, so just circle, and then G is a map from. So this is circle, whatever. C. So G is a map from C to this circle, another C to this circle. Okay. And this symmetry plus constant is just rotation. It's just rotational symmetry. And nether current associated with this rotation is this. So therefore, it's often called U1 current. This is called U1 current. And the stress energy tensor can be written in terms of J times J, U1 current. So this is called Sugawara construction, we will see. So this is the baby version of West-Zumino-Witten model, Sugawara construction. So this is the baby version of the why is baby? Because U1 is commutative. So it's commutative. Commutative means commutative. It's abelian group. Yes.
Did the range of the map G include the original part?
Range of map G includes original point. I don't understand the question. What do you mean? The range of the map includes original? This G?
The Z and the Z bar include the original part.
Or zero, you mean? Yes.
Then how does it point map to?
Whatever map, if you have R2, so you just have R2 times S1, any map, phi is just S1. G is just that R goes to S1. That's it.
It's like
What's wrong with this?
the 5Z bar means the angle of the point C.
Yeah. Phi is just angle. Phi is
But the original point didn't have.
I don't understand the question. It's just map from R2 to S1. What's wrong with this? Anyway, it's just map from R2 to S1. That's it.
I guess she means that if we understand it as a complex function, then understand G as a complex function, then at the original point it's not related.
Is it analytic? It's not analytic. Why?
But actually, the G can only take the value of the circle F1 after the map.
Yeah, can take the map.
Only can take the value of the
This one. Yeah.
It is not included the original point after the map.
You mean original point? This is not include. Of course, this is not
Yeah.
included as one.
Yeah.
Of course.
Of course, yeah. But their point on R2 have a map table has included in this map after before the map.
Of course.
Yeah. I think that is what it is.
Yeah. Okay. This includes 0. This includes 0. S1 is just only here. Everything else is just nothing. No, I don't understand the question so much. Anyway, so this is the baby version of S1, with the model, and we want to change this value from U1 to some the gauge group. No, not gauge group. Sorry, the Lie group. Any Lie group, non-abelian Lie group. But before then, I just want to. So before I generalize this action to non-abelian Lie group, I just introduce the so-called SU2 current algebra by free boson again. SU2 free boson, so current algebra. Okay. So we know that so we consider the map from the C to C to S1 with radius R. So we just consider this case, and so you guys just do the homework. Enjoy T duality. So this is nonlinear sigma model or whatever. Sigma model. It's not nonlinear. Sigma model, and enjoy the T duality. Enjoy T duality. So T duality is R goes to 2 over R. So that's we already seen the previous lecture, and also especially winding mode and also moment, Kawasaki moment. And I call it M, as far as I remember, M or N. I already forgot the. We know the under the T duality winding and the momentum, Kawasaki momentum will be exchanged. I call it N. I forgot. Anyway, momentum and the winding mode will exchange under T duality. That's what we have learned. And now we consider R is equal to square 2 is the self-dual point. Self-dual R is equal to square 2 is self-dual radius. That's I already introduced at that time. And let's see what's going to happen at this point. So at the self-dual radius point, we can introduce this following vertical operator I phi square 2 and j plus minus of z is equal to e to e plus minus I square 2 phi out. Okay. I think it used to be 2 over r or r. Here in the vertex operator involves the radius r, but once you put the r is equal to square 2, you can get this vertex operator. And now, so it's a good exercise to do. So it's a essential free boson. So you can just compute the OPE, the JZ, and j plus minus 0 is equal to plus minus j plus minus z of t. So this is your OPE you can compute. Indeed, this is the exercise in the next week. 1 over z squared plus 2j 0 and z, and then jz and j dot 0 is indeed 1/2. So this is exercise homework next week. You have to show this. And again, if you introduce it's very similar to spin jet representation or angular momentum. If you introduce j plus minus is equal to j1 plus minus I j2, and j is equal to j3, this OPE can be repackaged into JA, Z, JB, 0. Delta AB 1/2 Z squared plus I. So it becomes like this way. So here you can easily see it's very reminiscent of this. You can easily see that so it's very similar to what you learn in quantum mechanics, and the TA and TB commutation relation is equal to I and ABC and TC, where TA is a power matrix of 2. This is the SL2. So this is called SL2 Lie algebra. Indeed, this one is indeed called SL2 Lie algebra, or SU2, whichever you call it. Lie algebra. I will explain Lie algebra later, the definition. And in fact, if you define so if you define this J, the mode for this JA as mode expansion of the model expansion this one, and if you use this relation, you can show in the JA M JB and is equal to I its own ABC JC n plus n plus 1/2 and delta AB. So again, what you did to derive the Virasoro, so you get TTOPE to Virasoro algebra. Virasoro algebra. Likewise, if you use this JJOPE, you can derive this algebra. N delta n plus n. So this is also homework. Let's see. So if you only look at the m equals 0 part, m and n equals 0 part, you reproduce SL2 Lie algebra. Sometimes people call it SU2. Okay, I think let's go SU2 in my lecture. SU2 Lie algebra. SU2 Lie algebra, and if you focus on only 0 mode, m and n 0 mode, you get that. You receive SU2 Lie algebra, reproduce. But you have infinite many modes now. Okay, infinite many modes. M and n rounds for the integer value. So this is called SU2 level 1 affine Lie algebra. I will explain more in detail Lie algebra and so on later. And in particular, you can have, if you consider more generally, you can have the integer level k here in the, so it's called level. It's related to the Wessel-Witten model, or action of Wessel-Witten model. And then if you change to the k, so here it becomes k. And this guy is called level. This is indeed C value, and it's called level. And if you take my course in the differential geometry course, I already explained why the meaning of k in terms of Chern-Simons theory and so on, the relation between Chern-Simons and Wessel-Witten model. You already showed that k has to be integer. Anyway. Okay, so this is the of SU2, and so if you change to k, so you have a level k. So at level k. Okay, so this is okay. Let's study the highest representation of the SU2. And this OP is called current algebra. SU2 current algebra. Yeah, so self-their radius is. So this particular square root 2 is very important. This part of square root 2 is very important indeed. So you have to be square root 2 to get this OP. Yeah, otherwise you don't get the SU2 relation. So, and last 10 minutes I will do the very, very brief representation theory of this current algebra. And so we introduce the mode expansion, and then we can just again, we go back to plus minus notation. So J plus minus n is indeed J1n plus minus I J2n. And we impose Hermitian conjugate value is J minus n minus 1. And then okay, so this is Hermitian conjugate condition imposed, and then highest representation satisfy the following condition, and the highest weight representation of or states. Hj is defined as follows. So J03 acts on Hj equal to J Hj, and then J0 plus acts on H, and J is equal to 0. Of course, Jn H J acts on 0, where n is greater than 0, A is anything. So this is hardware state. And then, so this is this case, and of course you can just, of course the T is indeed, T is of course the defined 1/2, minus 1/2, 1/2 JJ, JZ in this case, and you have to show that the L0, so this is homework again in next week, J plus 1 is K plus 2, H and J. So this is the, you have to show the component dimension H, so this is equal to H. Component dimension H. So this is a high, sorry, I think this should be H. So representation of this affine Lie algebra is you start with h of j, and then you can act on the how to say creation operator or whatever called lowering operator in such a way that the for instance you can just act on the so you can just act like a, how to say, you can act on like a j minus 1, plus minus or 3, and to get the states, another state, hj, and so on. So you just apply whatever j minus 2 plus minus 3, act on h and j and so on. And so you can just have a highest state, highest weight state, and then just act the creation operator to get the representation, just to get the module. It's very similar to what's happening in Bernoulli module. So Bernoulli module, even Bernoulli module, you start with h and you act on minus 1, minus 2, and so on to get the Bernoulli module. The similar thing happening here. You start with the highest weight state that is annihilated by this annihilation mode. The n is greater than 0. But when 0 plus acts on, so it's similar to what's really happening in SL2C representation. You start with J, JJ state, and you have J, if you act how to say, raising operator, you get 0, right? And if you get the J minus, if you J minus, you get the J minus 1, and so on. Okay, do you remember? Essentially, J plus minus Jm is equal to some number times Jm plus minus 1. Okay, like this way. So if you act plus on J state, you get 0 because it's a raising operator. So there's no states greater than m equal to j. It's like this way. Okay, so that's what's really happening here. And then, so if you use this, if you use this the Hermitian condition in unitarity, we can just show that the just a moment. I think. Okay, so 0 greater than h j. So j minus 1 and j plus minus 1. Oh, I think let me erase this part. Act on h j. So you just do the, this is indeed, okay, maybe I should write down like this way. So this Hermitian conjugate j minus 1 plus, yeah, h j. So this is states, and this is indeed equal to h j, j plus minus, and the j minus plus h j. Okay. So since if you bring this one into here and act on here, you get 0 because I mean it's already this is plus 1. And plus 1 acts on j is equal to 0, right? So we already know. And minus acts on this one is also 0. So therefore, if you commute, you need this one. And if you use this one and the current algebra relation, you can use this relation to get the following. And then this is minus 2j plus k. So we now, if you do the computational relation, you get the j0, 3 minus k over 2 coming from here. So you just plug in, this is plus 1 and minus 1. And then you get the this relation. I don't think there is 2 here. Minus, I don't think there is 2 here. I think this is typo. But anyways, it doesn't matter. So essentially, some number times J03 minus K over 2. That coming from here. J03 coming from here, and K over 2 coming from here. Okay, so that's the, I think it depends on how you define plus or minus. Maybe 2 here, I don't remember. Some number. But it doesn't matter. It has to be 0. Okay? So some number times J over 2. Okay? Some number minus J. Some number times minus. So this has to be positive. So therefore, so if you assume the king, so therefore this has to be 0. So therefore J has to be less than or equal to K over 2. So it's the value of J is limited indeed. Okay. And moreover, so if you assume K is integer and J is a spin variable, so therefore we can just have J can take the value from 0, 1 half, 1, and K over 2. Oh, sorry, K over 2. Yeah. So this is the value that can take, the spin can take. And this is, let me continue. So you can have the Hj, and then you can act on the J0 minus, and then you can have H whatever J minus 1. You can have lowering operator J0 minus and so on. And of course, at the end of the day, J0 minus can only act on 2J times. Okay, H some states J0 minus Hj, and then J0 minus Hj, and then 2J. So in total, you have a 2J plus 1 states in the 0 mode. Okay, and if you apply, so you can go up by J0 plus and J0 plus. If you only look at the 0 mode, it's just SL2 representation, okay? SU2 representation, spin J representation. And then, but J can take, this spin, usually spin can take any value for SU2, but however, so affine Lie algebra, it can take up to K over 2. That's important. Okay, so that's some highest representation of SU2 current algebra. Okay, and then next time I will talk about introduce Lie algebra, Lie group. Maybe I will review a little bit more if you need it. And after that, I will talk about Western Middle Witten model. Okay, let's stop here. Just if you have a question, just tell me.